class, to the lesson titled 6.3 Pascal's Triangle. This is a really interesting application of sequences, and in this lesson you're going to discover some really neat patterns related to a special type of array or arrangement of numbers called Pascal's triangle. And so that's the first thing I want you to do, is actually construct this triangle, and it all starts with the number 1. What I want you to do is I want you to follow a certain procedure, and this is the procedure. You're going to start with the number 1, and this triangle throughout the right and left sides always has the number 1. Now, as we start to progress, here's how the triangle is formed. Each number in a position, with the exception of the values on the outside, as found by taking the sum of the numbers immediately above it. So for example, this number here is going to be found by adding the numbers directly above it to the left and to the right. So we're going to get 2 in this location. Again, on the outside we're going to get 1s, and now we're going to construct the next row, which has values 3 and 3 in the remaining positions. Each time we add a new row, we're going to add one more number, and again, just following that pattern. So I'm just going to have you pause the video and construct down to, maybe about the 7th or 8th row. All right, at this point, you should have an array of numbers which looks similar to this colorful pattern here. And if you went as far as the 8th or 9th row, you might have 1, 7, 21, 35, 35, 21, 7, and 1. This is a symmetrical arrangement of numbers. It has lots of really interesting patterns that we will explore in some detail. But for today, the connection we're going to try to make relates to something which at first wouldn't seem to have anything to do with the numbers itself or even sequences. But the application for today is going to be looking at something called binomial expansion, which we have lots of experience with. And binomial expansion, of course, 2 terms. Expansion involves multiplying or distributing, and we're going to be taking expressions in the form a plus b to the n. All right, so some of the questions we're going to be looking at here are, how does Pascal's triangle relate to this or help us to do these expansions? What I want you to do is, for the first, we'll say 4 expansions, which would be a plus b to the 0, where n is 0, a plus b to the 1, a plus b squared, and a plus b cubed. I want you to expand those out. Again, pause the video, expand those out. Remember, FOIL applies somewhat to this, first outside, inside, last, but at some point when you get to a plus b cubed, you're going to have to first evaluate the square of a plus b and then take that result and multiply by a plus b again. So it's going to take you a little bit of time, a few minutes to evaluate those. Pause the video at this time and then resume. Now I've worked out these expansions here. Now, a plus b to the 0 is the first one which we could look at. It's the simplest type, and of course that's going to be real easy because we can use exponent laws. All right, provided a and b themselves are not equal to 0, the answer there should be 1. So we get one term, and it's the number 1. A plus b to the 1 has 2 terms. A plus b are the result. A plus b squared, here we get 3 unique terms, just combined some like terms. And we would get 1a squared plus 2ab plus 1b squared. I'm intentionally putting some coefficients on here because there's patterns that are going to emerge. Now, going back to the original purpose of this activity, there were a couple of other things we're going to be looking for here. We're looking for some patterns in the expansion, specifically related to how many unique or like terms there are. A pattern in the coefficients on those terms, a pattern in the powers of the first variable or term A, and powers in the second variable or term B. And so if going back to our expansions here, we should have, for the a plus b squared, we've already looked at that. A plus b cubed has 4 unique terms with coefficients 1, 3, 3, 1. And you can see them as they appear on the screen. And the fourth expansion, you may not have gone that far, but I just took the liberty of doing that. And you actually get 5 unique terms. It takes a little bit of time to expand that out, but you get a to the fourth, all the way down to a final term which has no a term in it, or multiplier, and its value is b to the fourth. And again, taking note of those coefficients, they are 1, 4, 6, 4, and 1. So this is interesting because you've just constructed this interesting array of numbers called Pascal's triangle. It follows a very simple recursive type procedure where we're adding the values of terms in the previous row to get each term in the next row. And you'll notice that 1, 2, 1, that particular arrangement of numbers appears in the expansion of a plus b all squared, or in this slide, there are 3 terms, and those are the coefficients. In the expansion of something similar to a plus b cubed, we get the coefficients 1, 3, 3, 1. In the expansion of x plus y to the fourth, we get 5 unique terms with coefficients, as you can see there. And going even to the 5th power of x plus y, we get 6 unique terms with coefficients 1, 5, 10, 10, 5, 1, which, of course, if we were to go back to the triangle, guess what? Appears right here. Now, as it so happens, there's a specific way that we label numbers in this triangle. So I want to go back to this first slide and just spend a little bit of time talking about that. Now, there's something that you are already familiar with, which is term notation for sequences. We've used this a little bit already with explicit formulas and recursive sequences. For the Pascal's triangle array, we have what's called a general term locator. And this general term locator is described using a specific notation which has 2 labels or 2 property numbers associated with it, and they're separated by a comma. The first property number is the location of the horizontal row, n. The second number after the comma is the diagonal row, r. Now take note over here, all right? So how do these horizontal and diagonal rows get labeled? Well, as you might not have expected, we start with horizontal row n equals 0, which is the very first number 1 in Pascal's triangle. The first diagonal row is r equals 0, and that would be all of the numbers running along in between those 2 red lines. R equals 1 would group all of those values together, r equals 2, etc. So what we have is sort of the interaction between the horizontal row label and the diagonal row label. Now, one of the questions, the challenge question in this lesson is for us to try to answer this. What is the recursive formula to describe the general term? It's going to take a little bit of working with some of the numbers. And if we go now to a nice fresh copy of Pascal's triangle, we can try to answer this question. What is the recursive formula to describe the general term locator? All right, well, let's start with TNR. That is the form of the general term locator. If we were to label our diagonal rows, starting from 0 and increasing by 1, we don't have to go very far. We have enough values here to get this pattern established, and we would label our horizontal rows. N equals 0, n equals 1, n equals 2, n equals 3, and that's probably far enough. We would find, let's say, I'll choose this number here, this 3. All right, so first of all, I want you to just pause here and try to figure out what would be the notation that we would use to describe that particular number. So, all right, it's located in horizontal row 3, and it's located in diagonal row 2. So that particular number 3 there would be T, N is 3, R is 2. So that's T32. Now, where does T32 come from? Well, T32 is the sum of course, numbers directly above it, to the left and to the right, 2 and 1. Let's describe the 2 and the 1. The 2 would have general term notation, where n is 2 and r is 1. The 1 would have general term notation, n is 2 and r is 2. All right, so maybe the picture is starting to form here. To describe any particular number in the array, it looks like we're taking, to get T and R, looks like we're taking two terms. We're adding two terms together, so we can set it up like this. Now, in both cases, the value of n relatively is n subtract 1 for both of these. Now, in one case, the value of r is the same. And in one case, here, it's 1 less. So let's put this all together. Now, the order that we added these numbers is not important, but we'll just be consistent. If we're comparing 3 as being 2 plus 1, and 2 is T2 comma 1, and the 1 is T2 comma 2, and the 3 is T3 comma 2, then it would reason out that term n comma r would be found by adding term n subtract 1, r subtract 1, 2, n subtract 1, r. Okay, and in fact that would be the form of the general term locator. Looks a little bit like a recursive sequence because it is. It adds two terms which come before it, does not explicitly depend on n or r, and it requires you to know previous values. Now, there's some conditions on this, of course. We would have to indicate that initial term or terms are required, and in this case, we could probably, by loading in T 0, 0 equal 1, produce all the values in that. Because this recursive procedure that we have here would still allow us to find the outside terms, assuming we would assign 0 values to anything that comes outside of the array. All right, so I'll have you pause there. And at this point, we're going to go back and we're just going to look at just summarizing the properties that we found with this binomial expansion. Okay, here they are listed. So showing the first 6 binomial expansions where n equals 0 at the start, all the way down to n equals 5. We have the following properties. Relative to n, there are n plus 1 unique terms. That's the first thing we can take note of. So when the exponent is 5, we have 6 terms, n plus 1. The term coefficients are in order from the nth row of Pascal's triangle. Now keep in mind, that's not meaning in this case, the 5th row would actually be the 6th row because row 0 starts us off. All right, so keeping consistent with the horizontal row number n, the term coefficients are going to come from the nth row. Third pattern that we see is that the exponent on the terms containing a decrease in steps of 1 from n down to 0. Finally, the exponent on the terms containing the b value are going to increase, again, in steps of 1 from 0 to n. All right, let's just see if we can apply what we've learned so far. We've got an array of numbers called Pascal's triangle. We've discovered that there are certain ways of identifying where these numbers are found in a certain notation called the general term locator. It has to do with horizontal and diagonal rows. We've also uncovered the properties that describe the general term locator as a recursive formula. Some conditions, of course, on the variable letters N and R. There have to be natural numbers, and you'll notice that for any value in the Pascal's triangle, its diagonal row locator number is always less than or equal to N. And we could illustrate that by going to our triangle, and we could choose, let's say, the number 4, which would be found in horizontal row n equals 4. And we would notice that even if we got as far as 1, only then is the diagonal row number the same as the horizontal row number. But for every other number in that row of Pascal's triangle, the diagonal row number will always be less than the horizontal row number. So that's just one of those conditions that we have to put on our general term locator. Now, part of the resource package for this lesson is going to involve the Blackline Master 6-6, and in this case, you're going to just be exposed to some questions which get you looking at some patterning in the triangle and extend it a little bit. And I think for practice purposes today, if you understand how to create Pascal's triangle, which is a little bit of a challenge in itself, and you know some of those properties that we've already established, we're going to look at maybe just one example from this Blackline Master before we conclude the video. And the question I've chosen is just the first one, and it has us expanding each expression using Pascal's triangle. Now, we can look at something like a very obvious a plus b to the n. Now, it's not always going to appear as a plus b, and it's not always going to appear as x plus y. Sometimes the terms are numerical and sometimes they're variable. So for x plus 4 cubed, we would recognize that, oh, okay, this is going to have n plus 1 equals 3 plus 1, or that'd be 4, because n is 3 in this case. That's the exponent on the binomial. It'll have 4 unique terms. Our coefficients are going to come from, well, the third n value row in Pascal's triangle, which is 1, 3, 3, 1. That's fitting because we know we're going to have 4 unique terms, so coefficients we can list as 1, 3, 3, 1. We know the pattern is going to start with x to the highest power of 3 down to x to the 0. And we're going to start with 4 to the 0, and it's going to increase all the way up to 4 cubed. Now, the advantage or benefit of using Pascal's triangles, we don't have to actually do the distribution or the expansion. We can predict the values of the terms. What are the terms going to be? Well, the first term is going to have a coefficient of 1. It's going to have a power of 3 on x, and it's going to have a power of 0 on 4. Well, 4 to the 0 is 1, so we don't really need to include that, but just to illustrate the pattern of the exponents, we'll include it. The second term will have a coefficient of 3. And of course, we're following the pattern that the exponent on x, or our first term in the binomial, is going to decrease now, so this will go to x squared. And now we're going to be increasing the exponent on the second term in the expansion, which is, in this case, 4. So it's going to be 4 to 1. The next unique term is going to have also a coefficient of 3. This will have, again, decreasing power on x. Now will be x to the 1. The power on 4 is growing 1 at a time. This goes to 4 squared. The last term will have coefficient of 1. We have now exponent of 0 and x, and we have the highest exponent value of 3 on our 4. If we were to simplify this a little bit, this is still going to be 1x cubed. This is now going to be 3 times 4, which is 12x squared. 4 squared is 16 times 3, which is 48. 48 x's. And the last one will have no x's and the maximum power of 4 cubed, which is 64. It's a good idea just to verify that this would be our expansion result if we were to actually do this the long way. And this will just give us the confidence that this method is accurate. I'm just going to expand the first two binomials. This will give us x squared plus 4x and 4x and 16. We'll carry the x plus 4 factor through. Simplify. We're going to get, again, 3 like terms here. X squared plus 8x plus 16. Multiplied by x plus 4. Now at this point, the expansion of this is going to require us to multiply every term in the first, in this case, trinomial, by each of the terms in the binomial. So we're going to get an x cubed, we're going to get an 8x squared, we're going to get a 16x. Added to that, we're going to get 4x squared. 4 eighths is 32x, 4 sixteens is 64. Collect our like terms, keeping in mind, and here is 3. We're expecting 4 like terms, so we have an x cubed term. We have x squared terms here and here, which total to 12 x squareds. We have x terms here and here, which total to, as I said before, 48 x's, and we have a single numerical term, which is 64. This point pretty much concludes that what we need to explore with regards to this interesting array of numbers called Pascal's triangle. The assigned work for this lesson, which we'll work on tomorrow, will be this worksheet, and we'll be collecting one question from the textbook, which is found on page 378. Thank you.